So for this last section of Chapter 1, we're going to talk about using bijective arguments to show that two sets have the same size. So recall from an earlier section that a bijection f is a function from one set to another, so we'll say a bijection f from a set A to a set B is one which is both one-to-one and onto. And so there's just a natural way to match elements from the first set to elements to the second set. And in fact, this is a really primitive way of showing that two sets are the same size. So if you consider, for example, kids in a playground who maybe are very young and don't yet know how to count, but they want to split into two even teams to play a game, they don't really need to know how to count to know that they've divided the group into two even parts. As long as, let's say, these are your first 5 children and your second 5 children, you don't have to count to 5 to know that the groups are even, because if each child has exactly one partner sort of on the other team, right, if there's a one-to-one and onto way of matching up elements of the first set to elements of the second set, then you can be sure that those two sets are the same size. And so it's sort of a natural result to say if there is a bijection f from a set A to a set B, then those two sets are the same cardinality. They have the same number of elements. And in fact, this is actually how we define what it means for two infinite sets to have the same cardinality. And we'll see in some of the exercises that not all infinite sets have the same cardinality, but perhaps some surprising infinite sets are considered to be the same size as each other. Okay, so for sets A and B, if there exists a bijection, then we say that those two sets have the same cardinality. A good exercise, and we'll do one of these together now, but the rest you can try and maybe go through on your own, is to prove that for arbitrary sets A, B, and C, that A has to have the same cardinality as A, that if A and B have the same cardinality, then B and A have the same cardinality, and if A has the same cardinality of B, which has the same cardinality of C, then A has the same cardinality of C. And remember, in each of these, we should be using the definition of cardinality that we saw on the last page, because these are not necessarily finite sets. This seems super obvious for a finite set, but for an infinite set, it's not quite as clear. So if we wanted to prove, let's say the second result here, that if A has the same cardinality of B, then B has the same cardinality of A, then we're going to assume A and B have the same cardinality. So cardinality of A is equal to the cardinality of B. That is, we're going to assume that there exists a bijection f from the first set to the second. Right? A bijection just means that function is one-to-one and onto. Now we want to show that B has the same cardinality of A. In other words, we must prove that there exists a bijection, let's call it G, that goes the other way, right, from the set B to the set A. How are we going to do this? Well, just sort of to give ourselves, maybe we should have done this in the scratch work section, but if here's our set A and here's our set B, we know that there's a bijection going this way, from A to B. It's one-to-one, so two different elements of A have to map to two different elements of B, and it's onto, so every element of B has to get mapped to by something in A. So how do we know that there is a bijection that goes backwards? Well, one handy fact about bijections is that a bijection is guaranteed to have an inverse function. In fact, with the functions one-to-one, it has an inverse. And so there has to be essentially a backwards map, right, that sends everything in B right back to whatever mapped to it in A, or whatever element of A originally mapped to it. Right, there has to be an inverse function. And so, since f is a bijection, it has an inverse function f inverse that goes from B to A. And furthermore, that inverse function itself is guaranteed to also be a bijection as long as f is a bijection. Okay, and so we just let that function g that we're looking for be the inverse of f. And so, since there exists a bijection from B to A, that's what it means for B to have the same cardinality as A. Which is what we're trying to prove for this second exercise. For the first exercise, you just need to find a map from A to itself, which is a bijection, which should be simple enough. And for the third exercise, you need to find some way to get a bijection from A to C. Okay, so it's a good exercise. You should maybe pause and give that a try. But keep in mind that these three facts all together, the fact that A always has the same cardinality of A, that if A has the same cardinality of B, then B has the same cardinality of A, and then finally, if A and B have the same cardinality and B and C have the same cardinality, then A and C have the cardinality. These three facts, when put together, tells you that the cardinality is an equivalence relation on sets. This is something that you should maybe be familiar with from Math 180. Cardinality is an equivalence relation. Okay, and so looking at all the sets that have the same cardinality is a way of partitioning all sets based on how many elements that they have, right? It's reflexive, it's symmetric, and it's transitive. Now, these facts, of course, seem natural for finite sets, but the definition that we use for cardinality has some really interesting repercussions for infinite sets. And to just give you an example, consider the set of even integers. Okay, so even integers, this would be 0, plus or minus 2, plus or minus 4, etc. Would you say that there are fewer even integers than there are integers total? I'm going to call this set E just so I can talk about it a little bit easier. Fancy E. Remember, the set of integers would be the set consisting of 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. All right, so just looking at these two sets, which one of these sets seems bigger to you? Well, I mean, hopefully, it sort of looks like this one's bigger, right? Because the set of integers has all the same integers as the set E, and more, right? It also has positive and negative 1, which are not elements of E, and it has positive and negative 3, which are not elements of E. So this would suggest to us that even though both of these sets are infinite, that Z sort of seems like a larger set, because it has all the same elements of E plus more. But remember, the way that we define cardinality for infinite sets is we say that two sets have the same cardinality, they have the same size, if there is a bijection between them. If there's some nice way of mapping elements of the first set to elements of the second set in a way that's one-to-one and onto. And in fact, we can do this because for every integer, period, positive, negative, even, or odd, there's exactly one even integer which is twice as large. In other words, we can start with the set of integers, and we can map it to the set of even integers as follows. 0 gets mapped to 0 because 0 times 2 is 0. 1 gets mapped to 2, negative 1 gets mapped to negative 2. 2 gets mapped to 4, negative 2 gets mapped to negative 4. Now, how would we describe this? This would be the function that takes, should probably be clear here, f is a function from the integers to just the even integers defined by f of x is equal to 2x. Right? You take an integer, you multiply it by 2, and that's guaranteed to give you an even integer. Is this a bijection? Because if it is a bijection, well, that means that these two sets have to have the same cardinality. We consider them to be the same size infinity. And it turns out that, yes, it is a bijection. So how do we check that this function is a bijection? Well, there's sort of three things that we need to check. First of all, we need to know that this function is well defined. In other words, this function is actually going to take an integer and spit out an even integer. Right? For every integer input, we actually get an even integer output. So for every x in the domain, that's in integers, we have that f of x is an element of the codomain, is an even integer. This is what we need to check to make sure that it's well-defined. Is this the case? Well, sure, right? Let x be an integer. Then f of x would be 2x, which is, in fact, an even integer. That's how we define integers. It's anything that you can express as 2 times an integer. And so because this function is taking an input of an integer and giving me an output of an even integer, that's what it means for this function to be well-defined. It's actually mapping elements of the integers to elements of the even integers. So yes, this is well-defined. But remember, it has to also be one-to-one and onto. So how do we check that this function is one-to-one? Well, here we want to know that for any two x values, x1 and x2, in this domain, in the set of integers, if x1 and x2 are distinct, if they're different from each other, then their outputs, f of x1 and f of x2, are also distinct. They're also different from each other. This is how we check that the function is one-to-one. And again, yeah, this is going to be the case, because if you take two different integers, x1 and x2, the outputs are just going to be those same integers multiplied by 2. So this is true. Oops. This is true. If x1 and x2 are integers that are not equal to each other, then we would have that f of x1 is equal to 2 times x1, and f of x2 is equal to 2 times x2. And since x1 is not equal to x2, then 2 times x1 is not equal to 2 times x2. So f of x1 is different from f of x2 as well. Excellent. So this is going to be a one-to-one function. It takes two different inputs and gives me two different outputs. I still have to check that this function's onto. So let me go ahead and make a little space for myself here. Right, the last thing we want to do is check that this is onto. Right, remember, onto means that the codomain, the set of even integers, is equal to the range. In other words, every even integer gets mapped to by something in the domain. So we want to check that for every element of the codomain, for every even integer y, there exists, just do shorthand here, there exists an x in the set of integers in the domain such that f of x is equal to y. So if you hand me an even integer, I can figure out what integer is going to map to it. And I can, right? Hand me any even integer like 12, well, 6 is going to map to it. Hand me an even integer like 22, and 11 is going to map to it. In fact, I can figure out what number is going to map to it by just taking that even integer and dividing it by 2. Okay, so let's let y be an even integer. Then it's even, which means y over 2 is an integer. You can divide it by 2 and you'll still have an integer. And so we let the x that we're looking for in the domain just be that y value over 2. Then f of x is going to be equal to 2 times x, which is going to be equal to 2 times y over 2, which is equal to y, which is what we were trying to show. You can find an x that's going to map to that y. Well, you can, so yes, this is onto. And now we've shown that this is a well-defined function from the integers to the even integers, which is one-to-one and onto. That means this function is a bijection. Run out of space, so I'll have to wrap up my argument up here. So f is a bijection. And so we can say that using our definition of cardinality, the integers and the even integers have the same cardinality. It's the same size infinity. And again, that doesn't mean that all infinite sets have the same cardinality. We'll see in the exercises that there's ways to prove that there are bigger infinities, but they might actually surprise you where we draw the line. And so we'll talk about that when we talk about the exercises in class.